Okay, so in this unit, we're going to talk about advanced estimation of theta. And so far what we've done in the class is we started out by introducing this notion of maximum likelihood estimation, and we did a brute force maximum likelihood estimation. And so just as a quick refresher, I'm going to go back through that spreadsheet and talk about the formula and what we did and how it works, and just to get us back up to speed. You'll remember maximum likelihood estimation is about finding the theta that was most likely to have generated the particular pattern of responses given the item parameters. And the analogy we made is a little bit like going to a doctor and saying, here are the symptoms I have, and the doctor will think about the symptoms and maybe consult some references or what have you, and give you a diagnosis of the illness that's most likely to have generated that particular pattern of symptoms. That's sort of the basic likelihood case. The difference, of course, is theta is a continuous variable, whereas illnesses are discrete. But it's a pretty good analogy, I think. And we mentioned earlier on too that the actual process of going to a physician is very Bayesian, right? The doctor actually keeps in mind what the base rate is of different illnesses and uses that in the diagnosis as well. And so we're going to get there in this unit. We're going to talk about some Bayesian methods. But before we do that, again, I want to revisit this brute force maximum likelihood. And here's a quick summary of what we were doing before. So we laid out a spreadsheet where we have 5 items and we have item parameters, A, B, and C parameters in there. And we have a pattern of responses X, sometimes called U, actually, to make it consistent with the formula I'm going to show you. I'm just going to call it U. I don't know why people call it U. I'm not sure why that is, but that is often the convention. Whereas U is the observed response, it's either a 1 or a 0. And again, that's going to match up with these formula we see over here. So the first thing we do is in brute force maximum likelihood is to pick a bunch of thetas we want to consider as candidates for the estimate that's most likely to have given rise to this particular pattern of responses given the item parameters. Before what we did is we just made an Excel sheet. Nice thing about Excel is you can kind of copy and paste a lot of different values, and we just chose a handful just for illustration's sake. And the next thing you did, remember, we computed the probability of getting the item correct. And the probabilities were up here. So these are all the p-values. And the p-values are computed using this formula you see right here. Right, so the 3-parameter model, C plus the quantity of 1 minus C times 1 over the quantity of 1 plus the exponent negative, should be an A right there, negative A times theta minus B. So that's a little typo there in that formula. But that's a 3-parameter model, and we use that to compute these p-values, and then we also compute q-values. And if you'll remember, what we do to compute the likelihood is we just multiply together the p's and the q's, and we use the p's when the item was correct, and we use the q's when the item was incorrect. And I did that in Excel with just an if-then statement. I want to show you, though, you can actually make a mathematical formula that essentially is just an if-then statement, and you can see it right here. It's this likelihood equals the product from I equal 1 to k, and those are the items. So the product across items of p times q. And then it's got a couple other things there. So remember, that's what we did before. The likelihood was just the product of all these items where we're using p if the item was correct, and we're using q if the item was incorrect. And so this has a similar kind of effect. So U, remember, is the observed response, and it's always either a 1 or a 0. So let's think about what that means for a minute. Let's say the item was correct, so that U is a 1. So in this case, what we do is we take for item 1, we take the probability of getting item 1 correct to the first power. And anytime you do that, you get the same number. So if I just illustrate over here, if I type in equals 7 to the power of 1, you just get a 7, right? So any number to the first power is just itself, and that's why we don't usually write the 1 in there, but that's what's happening here. So we have the P for getting item 1 correct, and then we have Q, which is the probability of getting the item incorrect, to the 1 minus U. And again, U is 1, so 1 minus 1 is 0, so Q to the 0th power. And a similar kind of thing, if we type in 7, just a random number, to the 0 power, you always get 1. So you're multiplying the p-value times a 1, which is just the p-value for item 1. And then you go on to item 2 and you do the same thing. And so you do the part kind of off to the right here before you do any multiplication, just like we did up here, right? So essentially, if the item's correct, you get a p-value, and the q, just part of the right-hand side over here, just reduces down to 1. And if the item's incorrect, p to the u will be 0, so p to the 0 will be just 1 times q to the 1 minus 0, which is 1, which is just q, right? So essentially, this is just a mathematical way of saying use p if it's correct, use q if it's incorrect. And the nice thing about having a formula is you can actually code that into a computer program or something, and you don't have to do a bunch of like weird if-then statements. You can just write this formula in there. I wanted to show you the same kind of thing is true of the log likelihood. And remember the feature of logs is that we can take the log of the number and then sum them. So the log likelihood was just a sum of the p's or the q's, where you take the, obviously the log of the p or the log of the q. And the formula for that is very similar. It's the sum of everything off to the right here. So it's the sum of u times the log of p plus 1 minus u times the log of q. So again, if u is a 1, you end up with 1 times log of p plus 1 minus 1, which is 0, times q, which reduces to 0. So you end up with a p if it's correct, and you end up with a q if it's incorrect. If u is 0, it's incorrect, right? And so the same kind of thing, you got a formula here that does that if-then for you. And actually, you can see I actually did that formula in my math of the log likelihood. But let's just focus on likelihoods right now, just to keep it, I don't know if it's any simpler, but just to kind of be consistent. So this is what we did previously. Again, we used this likelihood formula. We tried a bunch of different thetas, and we computed the likelihood, and then we just picked the one with the highest number, right? This is just an if statement says if this is the biggest number in this column, write the word yes in here, and you can see that's what we did. And then we played around with a bunch of different values, and you see the estimate changes, and that's basically the brute force maximum likelihood estimation. You just try a bunch of different thetas, and we could do this. We could take this Excel sheet and make it a 10,000 rows long and have this increment by 0.001 if we wanted to, and that would work, but it's not very computationally efficient, right? So if you're doing this over and over and over, trying out 1,000 different values of theta is not really ideal, especially with something like a computer adaptive test where you're iterating that and you're updating theta estimate every cycle for every examinee. So we're going to find a better way to do it in this unit. We're going to use the actual maximum likelihood that's used by default in a lot of different computer software. We'll start with the case that's not Bayesian, and then we'll move up to a Bayesian case from there.